Good morning to all my dear students. Welcome to the another lecture in the Unit 1 Chemical Properties of the First Transition Series Part 2. This is the lecture number 6. We have discussed the first part of the chemical properties of the first transition series, in which the complex tendency, the colored ions and the relative stability of the oxidation state we have discussed. Students should have the knowledge of the first transition series, its characteristics, the properties, complex compounds, coordination number, geometry, relative stability of the oxidation state. Most of the elements in the first transition series are colored. So in the previous lecture, we have all these properties and the characteristics of the first transition series. The student should have the knowledge for this lecture. In this lecture, we are going to cover the following contents. The example of the first transition series complex is the most important complex we should discuss here: potassium permanganate, potassium hexacyanoferrate, potassium hexanitrocobaltate, and the magnetic properties of the first transition elements. What is the learning outcome of this lecture? The students will be able to understand about the chemical property, that is complex formation, with the most important examples of the first transition elements, and the magnetic properties of the first transition elements. The transition elements has the tendency to form the complex due to the presence of the vacant d orbitals. They can easily accept the lone pair of the electrons by the ligand. So we talk about the important complexes of the first transition series. The first we talk about the potassium permanganate. It is an important complex of the manganese. This is the middle element of the first transition series. It acts as an oxidant. It is a strong oxidizing agent which can be used in the laboratory for the volumetric analysis. So let's see the method of the preparation. How it is prepared? It is prepared from the potassium magnate. When treated with the sulfuric acid, it forms the potassium permanganate and water. The properties of the potassium permanganate: it is a purple crystalline solid, soluble in water. It gives out the oxygen on heating. That's why it is a strong oxidizing agent. Act as the oxidant in the laboratory and the industries. Frequently used in the volumetric analysis to find out the concentration of a reducing agent. In detecting the sulfite and the oxalate radicals. Another important application of the potassium permanganate, that it acts as a disinfectant in the treatment of the water. In the manufacturing of the other synthetic organic compounds, it acts as a raw material. The next important complex of the iron, that is potassium hexacyanoferrate, K4FeCN6. How it is prepared? It is obtained by reacting the ferrous sulfate with the excess of the potassium cyanide. So the first step, it goes with the reaction to form ferrocyanide. which again react with the excess of the potassium cyanide to form potassium hexacyanoferrate. It is also manufactured from the crude coal gas. So, by the two methods, it is generally prepared. Potassium hexacyanoferrate is a lemon yellow crystalline water soluble solid. It decomposes on heating. So when it goes for heating here, we have the sign of heating on the arrow. It represents the action of heating. So it decomposes into the iron carbide, potassium cyanide and the nitrogen gas, which further decomposes to the iron, potassium cyanide and again the cyanide. It gives bluish white precipitate with the zinc salt. It is used for the identification of the zinc in the inorganic radical testing. So it can be easily form a white precipitate which indicate the presence of the zinc. The uses of the potassium hexacyanoferrate in preparing the carbon monoxide gas. It is used in preparing the Prussian blue pigment, in detecting out the copper, iron, zinc and calcium inorganic radicals, in the manufacturing of the potassium ferricyanide, that is K3. The potassium ferricyanide is prepared from the potassium ferrocyanide. So in the manufacturing of potassium ferricyanide, that is K3FeCN6. So it's the another complex. We have the potassium ferricyanide, which is prepared by potassium ferrocyanide. The next important complex of the cobalt, that is potassium hexanitrocobaltate 3, K3CONO2. It is also called potassium cobaltinitride. If we see the method of the preparation, it is prepared from the sodium hexanitrocobaltate with the potassium salt, that is potassium chloride. So it can easily prepared out by the sodium complex. It can easily released and the sodium chloride is formed and we have the complex potassium hexanitrocobaltate or cobaltinitride. Let's see the properties and uses of the cobalt nitride complex. It is water soluble yellow crystalline solid. It is decomposed by the acid and the base. It is used as a yellow pigment in the famous name, that is Indian yellow or a cobalt yellow. So it is used as a pigment in the various paints. In printing the porcelain blue, So these are the important applications of the cobalt nitride complex. Now we see the magnetic property of the first transition elements. The first transition elements show different kind of the magnetic behavior when they are placed under the influence of the magnetic field. When the substances or the elements are attracted by the magnetic field, when they are placed under the influence of the magnetic field, such type of the attraction and such type of the behavior which is attracted by the magnetic field is called paramagnetic property, and the phenomena is called paramagnetism. And paramagnetic property is only shown when the substance or the elements contain one or more unpaired electrons. So we can say if the substance or the element is having the unpaired electron, so it is attracted by the magnetic field up to when the magnetic field is influenced to that substance or the element. And when a substance acquires a permanent magnetic moment, even if the removal of the magnetic field takes place, still they show the attraction, such type of the behavior, that is, we can say having the permanent magnetic moment, that is the behavior called ferromagnetic. And in the first transition series, iron, cobalt, nickel, they are having this behavior, ferromagnetic behavior. The phenomena is called ferromagnetism. And the third type of the behavior, which we can see, that the substance which are repelled by the magnetic field, they are called diamagnetic substances. And such type of a phenomena is called diamagnetism. And such type of a behavior is caused by those substances or the elements which contain only paired electrons. So in the first transition elements, we have the iron, cobalt and nickel. They are the ferromagnetic substances, retain their magnetism even after the removal of the magnetic field. Strongly shows the attraction which is having the permanent magnetic moment. Now we see the magnetic property in a complex. Let's take an example of manganese having the atomic number 25. What is its electronic configuration? 3d5, 4s2 and 4p0. If we see its electronic configuration, so we have d5, this is the d orbital, we have s2, 4s2 and p3 orbitals are vacant. So this is the electronic configuration. Now when the manganese loses its 2 electron and become the manganese ion, okay, 2 plus. So 2 electrons are removed from the outer orbital, that is 4s, okay. So in the excited state, when the 2 electrons are loose by the manganese, it becomes empty s orbital and we have the empty p orbital. Now when the ligand approaches to this manganese ion, that is Mn2 plus, it depends on the strength of the ligand approaching towards. So how the complex is formed, it depends on the strength of the ligand. Suppose a weaker ligand like bromide approaches towards this manganese ion. So weaker ligand do not affect the electrons which are present in the manganese, that is half filled d orbitals. No effect is found when the weaker ligand approach towards the central metal ion. But if the strong ligand approaches, the electrons adjust themselves to have some effect. That's why it forms different kind of the complex, that is inner orbital complex, in the presence of the strong ligand. And when the weaker ligand is approaching, no effect is found, that is formed outer orbital complex. So here, when a weaker ligand approaches, no effect is found in the d orbital arrangement of the electrons. It undergo the vacant orbital hybridization like s and p3. So sp3 hybridization takes place to form 4 new hybrid orbitals. Understood? And which can easily accept the lone pair of the electron, that is 4 bromide ion can easily come up and form the complex. So here the complex ion manganese is linked with the 4 bromide ion, which is exert as the weak ligand field on the metal ions orbitals. As a result of this complex, how many unpaired electron is there? 5 unpaired electrons d orbitals which remain unaffected, and 1s and 4p empty orbitals of the metal ion hybridized to produce 4 new sp3 hybrid orbitals, giving out which type of the geometry? That is tetrahedral structure of the complex ion. If we see its magnetic moment, the calculated magnetic moment of this complex is nearly found, that is 5.92 Bohr magneton, which indicates the presence of 5 unpaired electrons. So experimentally, its magnetic moment which is found, which clearly represent in the complex formation, that in this complex there are 5 unpaired electrons. That's why its magnetic moment is 5.92 Bohr magnetic. Which type of the magnetic behavior is shown by this complex? This complex show the paramagnetic behavior, because due to the presence of either one or more unpaired electron is present, then which type of the behavior it shows? It shows paramagnetic behavior. So it is having the proof that this complex is having 5 unpaired electrons. It shows the paramagnetic behavior, and it is having the excess unpaired electron. That's why its magnetic moment is also coming in excess 5.92 Bohr magneton. If that is the situation, the tetrahedral structure of the complex is confirmed involving s and p orbitals. So the complex formation is taking place by the involvement of the s and p orbitals, and the d orbital electrons remain unaffected because the ligand which is approaching towards the central metal ion, that is weaker, and because of that such kind of the complex outer orbital complex is forming, and this is showing the conformation of this complex and its geometry. So on the basis of the strength of the ligand, the complexes which are formed and which type of the behavior it is shown, it can be explained. Similarly, for the complexes having the coordination number 6, the 6 ligands are attached to the central metal ion, and we can predict whether the complex is outer or the inner orbital complex depending on the weak and the strong ligands. If the weak ligand is approaching, that causes the outer orbital complex, and if the strong ligand is there, then we have the inner orbital complexes. For example, the cobalt complex is the outer orbital complex with the water H2O neutral ligand, and the same central metal ion with the ligand NH3, that is the stronger ligand. It is forming the inner orbital complex. The same central metal ion is there. And what is the difference? The difference is in the strength of the ligand, okay, which involves the sp3d2 and d2sp3 hybridization. So d2sp3 is inner and sp3d2 is the outer, okay. So it goes for deciding its unpaired electron and its magnetic behavior. So we can easily understand the complex's magnetic behavior by the formation of the complexes. So it can easily predict out whether the complex and the substances or the metal ions having which kind of magnetic behavior. So this is all about the first transition element properties. These are the references for this topic: the Concise Inorganic Chemistry by J.D. Lee, the Chemistry by the Tandon, M.M. and Tandon, Inorganic Chemistry by J.E. Hui. You can go for the reference and the textbook for the topic. Thank you and take care.